Alright, so section 4.9 deals with matrix transformations from the vector space Rn to the vector space Rm. So first of all, what is a transformation? A transformation is just basically a function that maps elements from one vector space V into a vector space W. So the transformation normally has that form. And remember, a function is a rule that assigns each point in the domain one unique point in the codomain. The function is not allowed to send a point V to two or more different points in W. It's only allowed to send it to one unique point. Right, so as I said, V is the domain and W is the codomain. Now note, in the case where V is equal to W, just take note that the textbook refers to a transformation as an operator. Now, in this section, we consider transformations from Rn to Rm. Right, so they look like that. So we're going to look at very specific transformations. Right, so then a linear system, AX equals W, where X is an Rn and W is an Rm, and A is an M by N matrix, we can view that as a transformation. It takes a column vector X in Rn and it maps it to a column vector W in Rm. And we do this by simply multiplying the column vector X on the left by the matrix A. Now we're going to look in this section a lot at that type of a matrix transformation. So that is called a matrix transformation, and we denote it by T subscript A. The subscript A, the A deals, signifies the matrix that you are multiplying with. So again, T subscript A X bar, it takes X bar and it multiplies on the left with the matrix A. So the matrix transformation TA is called the matrix transformation TA is called a multiplication by A, and a matrix A is called the standard matrix of this particular transformation. Right, so we can go and look at properties of matrix transformations. So Theorem One gives us some properties. For every matrix A, the matrix transformation TA from Rn to Rm has the following properties for all vectors U and V in Rn. So first of all, it always maps the zero column vector to a zero column vector. And this is obviously, it's easy to see that because if you multiply a zero column vector with a matrix A on the left-hand side, you're going to get the zero column vector on the right-hand side. If you take a scalar multiple of a column vector and you multiply that on the left with matrix A, that's the same as taking the column vector U and multiplying that with the matrix A separately on the left, and then taking that whole column vector and then multiplying that with a scalar K. So that is easy to see. Then also you have distribution over the sum. So take two column vectors, add them together. If you multiply on the left with the matrix A, you can clearly see that if you multiply the matrix A with the sum between two column vectors, we can easily apply the associativity rule. So if that is clearly the sum between the respective matrix products. Okay, so that in itself is we had that this is that's T of A in the point U bar plus V bar, okay, and that is T in the point A U plus t a in the point V. Okay, so that is easy to see. And then the last property as well, that's easy to see that as well, because property 4 follows from this property, and it follows from that property. Okay, so those are properties of matrix transformations. Okay, so a transformation from Rn to Rm is said to be linear if it has the following properties. If you let t act on a scalar multiple of the vector, then that's the same as letting t act on the vector itself and then multiplying that with a scalar k. The same is, similar truth. Right, and then the second property is that if you let t act on the sum between two vectors, it's the same as letting t act on each vector individually, each vector in the sum, and then adding the two results up. So when you have those two properties, we say that a transformation is linear. Now it follows from Theorem 4.9.1 that every matrix transformation is a linear transformation. Right, now if we go back to Theorem 4.9.1, you can see that for this matrix transformation has that scalar property. So there we've got that scalar property, and it also distributes over the sum between two vectors. So 2 and 3 implies that every matrix transformation is a linear transformation. Right, so the converse is also happens to be true, and that is Theorem 4.10.3. Every linear transformation is a matrix transformation. Now, why is that true? Right, so there's our linear transformation T. It takes a vector with n components and it maps it to a vector with m components. Now remember, T is assumed to be a linear transformation. All right, so we can write the vector v1, v2 up until vn. We can write it as a sum between scalar multiples of the standard unit vectors. Now T is a linear transformation, so it distributes over scalar multiples and sums of vectors. So we can replace T with the following. Right, so again, T distributes over the sum, and each one of the T's within the respective unit vectors, they all map, those unit vectors map to specific points within the space Rm. So we can denote them each with by a vector with m components. Right, so in matrix notation, we can write that linear combination as a linear combination of these column vectors. All right, and that then basically becomes, right, we can go and write it as a product between two matrices, a product between two matrices. So here on the right hand side, you've got your vector that you end up with. Here's the vector that you start with, and this is the standard matrix, which takes my vector in Rm to my vector in takes my vector in Rn and maps it to a vector in Rm. So I've basically written T as a matrix transformation. Right, so my transformation, my matrix transformation, we can just go and write down the form of that. So the transformation T is equivalent to the transformation subscript A in the vector point u bar, and that gives me w bar, where A is the standard matrix. U is this matrix here, vector, and W is that matrix there. All right, so we've basically shown that T is actually an actual fact equivalent to just a matrix transformation. Right, next we are asked the following example. What they ask us there is find the standard matrix for the transformation from R2 to R3, and it's defined by the equations, by those three equations. Okay. So this is not a terribly difficult thing to do. We're going from R2 to R3. Right, so there's my function, and those are the transformed points. So it takes each point x1, x2, and it manipulates it to get a point in R3. Essentially, T takes the vector x1, x2, and it maps it to the vector w1, w2, and w3. Right, so writing that down in matrix notation, we take our vector x1, x2, we take our vector w1, w2, w3, and we want to find a matrix that will transform the point x1, x2 into the vector w1, w2, and w3. So what must that matrix be? So we have a 3 by 1 matrix on the right hand side, and we've got a matrix multiplied by a 2 by 1. So this matrix obviously has to be a 3 by 2 matrix. And what's going to give me that is this one here, that matrix there. So you can clearly see if you multiply those matrices out, you get the point W1, you get the point W2 as well, and you get the point W3. So the standard so the standard matrix for this transformation is the matrix A. Right, next we asked, given to do another example, they asked me find the standard matrix for the transformation from R3 to R2, and it's given by this transformation takes a vector and it maps it to a vector in R2. Right, so there's my function, my transformation T, and I want to find the standard matrix for that transformation. So I take the vector x1, x2, x3, and take the vector x1 plus 3x2 and x1 minus x2, and I want to find the matrix that I have to multiply with a vector x1, x2, x3 to get whatever I have on the right hand side. So I've got a 2 by 1 matrix there, and I'm on the right hand side, and on the left hand side I have to multiply with two matrices. The one is 3 by 1. So what must I multiply with a 3 by 1 to get a 2 by 1? A 2 by 3 matrix, and the matrix that's going to give that to me is going to be that matrix. Okay, so the standard matrix then becomes the matrix A. Okay, so that's the standard matrix for this transformation. Right, so let's look at this example. Here they ask us, they look at a transformation from R2 to R2, and it's the transformation that takes a point in the xy plane, and it reflects that vector about the y axis. So we are asked to show that this transformation T is linear. Right, so there's our reflection along the y-axis. Right, so we're reflecting it in that way there. Right, so to show it's linear, we need to show two things. We're going to first show that t distributes over the sum between those two vectors. We first take t, for argument's sake, in the point x, y. Right, so for argument's sake, we take t in the sum of those 2 points. Right, that we can write as, okay, and that we can write as, right, and furthermore, we can further go and manipulate that term a little bit and write it as, right, then we can write that as, okay, and we can see that the first property of linearity holds. T distributes over the sum between two vectors. Now taking a t on a scalar multiple of a point xy, that is going to be then translate into taking t and letting that act on the vector alpha x, alpha y, and we know what the transformation does to that. It takes the negative of that, alpha x, and it maps it, it maps the y value to the y value, and that we can write as alpha multiplied with the vector minus xy, and that is equal to alpha t in the point xy. Alright, so clearly this transformation is a linear transformation. Right, next we are asked to find the standard matrix for a t. Right, so taking the transformation t, we get the following. We can write the vector x, y as a scalar, well, as a sum between two scalar multiples of those standard unit vectors. Because we know the standard unit vectors form a basis for R2. We know that t is linear, so t distributes over the sum between two vectors, and that scalar multiple property also holds. So that we can replace with. Okay, so we get that there, and then from there, right, so there we've got our expression for t in acting on the vector xy. So basically, it all boils down to what is the image of t in on that standard unit vector, and what's the image of that. So this whole transformation t is actually determined by what these two values are. So we need to go and look at what those values are. So we know what t does to 1, 0. It maps it to the point minus 1, 0. And we know what t does to 0, 1. It maps it to 0, 1. Right, so taking all that together, we see that the matrix that is going to transform the vector xy into the vector minus xy is going to be, the matrix is going to be minus 1, 0 and 0, 1. So that is the standard, that's the standard matrix that's going to do that for me. Alright, so let's look at this example. Here we are transforming the point P into the point Q. So you're taking the vector formed by the point P in the origin, and you're projecting it on the vector Q formed by taking Q with respect to the origin. So we can see clearly here that we're reflecting the point P, we're reflecting it about the YX plane. Right, so so now the question is, what is the matrix that we, what is the standard matrix for this transformation? Right, so remember a linear transformation is pretty much determined by, in this case, by the standard unit vectors. Because we previously looked at an example. Right, so there, if we look at the transformation T, it acts on that vector xyz. We can write the vector xyz as a linear or as a linear combination of the standard unit vectors, and then distributing T over the sum, because T is a linear transformation. So we get this this linear distribution. Remember, it's a linear transformation, so it distributes over a sum, and it also distributes over scalar multiples. So essentially we pretty much are just interested in the values of T in the standard unit vectors, because essentially they are the ones that will generate the whole, that will generate all the points x, y, z. So what are those values? All right, so T maps the vector 1, 0, 0 to 1, 0, 0. It maps the vector 0, 1, 0 to the vector 0, 1, 0. And it maps the vector 0, 0, 1 to the vector 0, 0, minus 1. So now we need to go and construct the standard matrix from that information. Right, so we take my vector x, y, z. Then I take the vector where I want to end up, which is that vector there, and I ask myself, what is the matrix that I have to multiply on the left-hand side to get to my right-hand side? And it just so happens that this matrix that will give that to me is that 3 by 3 matrix. Okay, and in the notes, they look at a whole lot of different projections along the ZX plane. They also look at projections along the ZY plane, and also on the XY plane. So the process of getting those matrices are exactly the same as the one I've just demonstrated. Okay, so let's look at this question. Here they ask us, find the standard matrix for the transformation T that rotates P to Q through theta. So what they're actually asking there is, you start at the point P, and then you're rotating it through to Q, but through the angle theta. So you're going from P to Q through the angle of theta. Okay, so let's just relabel it. So there, let's call that whole, let's call that angle theta 2. So we've basically have that whole angle theta 2. Okay, and let's call this angle here theta 1. Alright, and let's just call, for argument's sake, the distance between the origin and the point P, let's call that R. Okay, so what we're going to do is we're going to find the polar coordinate representation of the point W1, W2. So there's the coordinate representation, and the same is true for X and Y. So that becomes, right, So there we have that. And now applying our trig identities, we have to find an expression for W1 in terms of x and y, and an expression for W2 in terms of x and y. So let's look at W1 first. Right, so taking W1, we obtain. Right, so we can replace theta 2 with theta 2 minus theta 1 plus theta 1. Right, so that we can then go and replace cos theta 2 minus theta 1 plus theta 1. We can use the our trig identity, and so replace that cos term with cos that minus that, cos of that angle, cos theta 1 minus sine of that angle times sine theta 1. And again, doing the back substitution, replacing r cos theta 1 with x, and replacing r sine theta 1 with y, we obtain this expression. Right, next we take W2 and we perform the same idea with that. We can replace sine theta 2 with, okay, and then applying our trig expression for sine of the sum between two angles, we get. So we obtain that expression, and remember theta 2 minus theta 1, we can replace that with theta. Recall that that is what the angle theta is. So there we go, the expression for W2. So putting all of that together, we get, so there we have the two expressions. We can go and write this now in matrix notation, and that will look like, so there we've got our first component. There we've got our second component, our third component, our last component, right? Right, so there we've got our expression in matrix notation. So now I want to transform the point W1, W2 to the point x, y. So I want to find the matrix that I have to multiply with W1, W2 to get me to the point x, y. Alright, so we can then solve for the point x, y quite easily by inverting the matrix. Right, so there we just need to find the inverse of the matrix, and that is, right, so there we've got the transformation matrix that transforms the point W1, W2 to the point x, y. So we've rotated P through the angle theta into the point Q. So let's say we were to reverse this transformation. So let's say we want to find the transformation from the point Q right back to the point P. Then what would that transformation matrix look like? So there we have the two cases. So transformation from P to Q as given by that given matrix, and then the transformation back from Q to P as given by that matrix. Alright, so again in the notes you guys will see, and in the textbook as well, you've got some examples of finding standard matrices for specific transformations. Specifically here we see the transformation about the y-axis. There we map the point xy to the point minus xy, and we did derive in an example the standard matrix. Then also the reflection about the x-axis. That's easy. There my y goes to minus y, and that's going to change the standard matrix slightly. And then also we've got reflection about the line y equals x. So the point y, xy is mapped to the point yx. And that's also going to influence the standard matrix. So doing all of this, you follow the exact same procedure there. What is important is identifying the images of the standard unit vectors, because we can write each point xy as a sum between or you can write each point xy as a linear combination between the standard unit vectors. Right, now in R3, again, here you've just got an extra component, and this one is the one we did, where you basically you are taking the point xyz and you're reflecting it about the xy plane. And that is an actual fact in the example we did. That's the standard matrix you get. Then you can look at other variations. You can look at the variation where we go about the xz plane, which is that one there, and also the reflection about the yz plane, which again is a straightforward argument to follow to get to that. Then we go back to chapter 3, which is on projections. Here we've got the orthogonal projection of a point onto the x-axis. There you make y0. It's an easy process to find the standard matrix there, and then the projection on the y-axis, which in this case we map x to 0. Then you can also get projections in R3. There you get an orthogonal projection onto various different planes. You can get it on the xy plane, the xz plane, or on the yz plane. If it's the xy plane, you are making z0. If it's on the xz plane, you're making y0. And if it's on the yz plane, you're making x0. Again, it is a case of identifying what the values of that you find when you apply t on the standard unit vectors, and that is what is going to determine your standard matrix. All right, so the example we just did relates to page 12 of the notes. There you guys will see rotation through angles theta. So here we have rotation from xy to w1, w2. And remember, in the previous example, the standard matrix we got there, the one that gave me that transformation is the matrix cos theta minus sine theta cos theta. And we also derived rotation in the opposite direction from w1 w2 to xy. The last theorem, it just states that if you've got two, it gives you a condition of when the standard matrices of two transformations are the same. So if you have the one matrix transformation TA and the other matrix transformation TB, then if it happens that they are the same, both of them are the same for every column vector x in Rn, then those matrices have to be the same. Now, again, this is not difficult to see. Right, so there we've got the two representations. So take on the one hand TA and TB, and both of these matrix transformations, they are equal to one another for every x vector. So I can plug in any x in there that I want, and I'm always going to get equality. Let's see what happens if I make the vector. The unit column vector with the first row equal to 1 and all the other rows equal to 0. Right, now multiplying those out, we get a column vector, and you can see we get the first column of this matrix, and we get the first column of this matrix. Right? Now we said that for every vector x, TAX is equal to TBX. Right, so there we see we've got equality between these two things, which is said for every vector x. And so we've got equality between the column vectors of both that matrix and that matrix. Right, let's take the next vector, the vector with 1 in the second row and 0 everywhere else. If you go and multiply that out, we are going to get we're going to get the second column there. Right, and the other matrix, we're also going to get the second column, so we're going to get the second column there. Right, there we go, and again, we know that equality holds with respect to all the vectors, right? So there, t in that vector is all going to be the same. T in that vector, they are always going to be the same. So therefore, we have that the second column of this matrix is the same as the second column, and we also have the first columns are the same. So you can follow this process through right up until the last type of vector. Right, so take the last vector, and again, we're going to pretty much get, we're going to get again we're going to get the last column of the matrix, right, and the other matrix. Right, so we find that the last columns of these two matrices, the last columns are also the same. So column-wise, both those matrices are the same. So therefore, what can we say? We can say that both those matrices are going to be the same. Right, so both the standard matrices for those two transformations are going to be the same.